ตราจารย์ดักลาส ดี โอเชรอฟได้รับรางวัลโนเบลสาขาฟิสิกส์เมื่อปีค.ศ. 1996 จากการค้นพบความเป็นของไหลยิ่งยวดในธาตุไอโซโทปฮีเลียม 3 ถือเป็นการค้นพบที่เป็นประโยชน์ต่อวงการวิทยาศาสตร์เป็นอย่างมากและก่อให้เกิดการศึกษาและวิจัยด้านของไหลยิ่งยวดซึ่งมีประโยชน์ในการศึกษาปรากฏการณ์อื่นๆในธรรมชาติเช่นการศึกษาการก่อตัวของกาแล็กซีในยุคเริ่มต้นของจักรวาลปัจจุบันศาสตราจารย์ดักลาส ดี โอเชรอฟอายุ 67 ปีเป็นศาสตราจารย์สาขาฟิสิกส์มหาวิทยาลัยสแตนฟอร์ดซึ่งในครั้งนี้ท่านได้ให้เกียรติมาบรรยายเรื่องความก้าวหน้าทางวิทยาศาสตร์เกิดขึ้นได้อย่างไรและวิทยาศาสตร์เปลี่ยนชีวิตเราอย่างไร
I'm promised to give you a talk today, and I'm hoping you'll find it interesting. Okay, so this is the Grand Canyon at sunset, and what I wish to say is that those discoveries that most change the way we think about nature cannot be anticipated. How then are such discoveries made, and are there research strategies which can substantially increase one's chances of making such a discovery? And of course, I have to think the answer to that is yes, or I wouldn't have asked the question. So let me illustrate this with a linked chain of discoveries and inventions, starting with one of my great heroes, this gentleman here, and I presume that everyone knows who this is. This is Heikki Camerlionis, who was the first person to liquefy helium, and I dare say without his contributions I probably wouldn't be speaking here today. Camerlionis first liquefied helium in 1908. This was helium-4, the commoner isotope of helium, although helium is not very common. In just 5 years later, he received the Nobel Prize for Physics. And I suppose you can imagine that he's smiling at us, but in fact, I don't think that Camerlionis, I think he seldom smiled. So what happened was that there was a competition between Dewar and Camerlionis to see who first could liquefy the lightest and most inert of the atmospheric gases. And it looked like Dewar had won when he succeeded in liquefying hydrogen. Of course, hydrogen is the lightest element, but it's certainly not the most inert. So Camerlionis, there was only one element left to liquefy, and that was helium. Helium was very scarce at this time, but eventually Camerlionis was able to get enough helium that he could attempt to liquefy it. And Camerlionis decided to answer some other interesting question of the day that he could with this very spectacular set of refrigeration devices that he had built. People were arguing about what would happen to the conductivity of a very pure metal if one could cool it to absolute zero. One school of thought was that as you cooled it, you eliminated the lattice vibrations that scattered the conduction electrons, and so gradually the electrical resistance would slowly drop towards zero, whereas the other school of thought believed that at some temperature the conduction electrons, which are free to roam around the interior of the metal, would recondense on the ions from which they had come, and all electrical conductivity would cease. So Camerlionis obtained a very pure sample of mercury and gave it to his associate. I actually don't know if Gilles Holst was his graduate student. Camerlionis was not of the habit of including his students' names on his research papers. So it's a little bit difficult to tell, but so I hear some hissing in the audience. It must be a graduate student's hissing. Anyway, so Gilles Holst is measuring the electrical resistance. Those are the green points. This is the scale of resistance from 0 ohms up to 2/1000ths of an ohm, very small resistance, electrical resistance. And temperature goes from 4 Kelvin to 4.5 Kelvin. And as you can see, as he is cooling it, in fact, the electrical resistance is dropping. But then at a temperature of about 4.2 Kelvin, there was a nearly discontinuous drop in the electrical resistance to a value that was less than 10 to the minus 5 ohms, essentially zero electrical resistance. This, of course, we look at this and we now know that this, in fact, was the onset of superconductivity. The metal that Camerlionis had given Geelholz was mercury, which is a very good superconductor at low temperatures. So, in fact, this was the first observation of superconductivity. And I don't know if this is exactly what Camerlionis got the Nobel Prize for in 1913, but I suppose it had something to do with that. I dare say that superconductivity has been studied in multiple places around the world ever since that time. It's a phenomenon that has fascinated physicists for a long time. So now you see what I actually am is not a physicist, but a photographer. This is a small part of the Iguazu Falls at the border between Paraguay and Brazil. And I like to illustrate the ideas in my talks with distracting photographs in the background. So the process of advancing science often leads to inventions and technologies that directly benefit mankind. However, it is impossible to know from where the advance will come that might solve a particular problem facing mankind. Consider, for example, nuclear magnetic resonance. And I don't mean to say that nuclear magnetic resonance is a problem facing mankind, but a solution to problems facing mankind. So nuclear magnetic resonance were invented by these two gentlemen actually in 1946, just at the end of World War II. The two gentlemen are Felix Bloch, who was a professor at Stanford University. And I dare say Felix Bloch was a rather crusty old man. Even though I'm a professor at Stanford University, I never met Felix Bloch. He died by the time I became a professor there. Ed Purcell was a professor at Harvard and a very kind and gentle and warm person whom I dearly loved. And I'm afraid he's not around either anymore. But these were the two gentlemen that invented NMR. And so, of course, they got the Nobel Prize just 6 years after their development, their invention, and so they went to Stockholm and got their Nobel Prizes. And, of course, then the press descended on them. Of course, they were asking these gentlemen to explain nuclear magnetic resonance, which is a very complicated process involving the precession of nuclear spins having magnetic moments and magnetic fields. And after a while, the press would give up because they couldn't understand any of this. And so they said, just tell us what NMR, nuclear magnetic resonance, might be good for. And Felix Bloch is supposed to have said, damn little. His idea was that they were measuring the distribution of charge into atomic nuclei, and this had nothing to do with applications. And Ed Purcell, who was a kinder, gentler man, said, well, perhaps one can use nuclear magnetic resonance to calibrate magnetic fields. Now, this is what the visionaries that invented NMR had to say about it. Let's see what actually transpired. Well, first of all, this is a spinning top in a gravitational field, and this is basically explains what Felix Bloch and Ed Purcell couldn't explain to the press, but so I think we can blip over this. And now we're looking at an organic molecule in solution, probably aqueous solution, and specifically we're doing nuclear magnetic resonance on the hydrogen nuclei, the protons, and what one finds is in fact that they did all the protons, the hydrogen atoms, do not come into resonance at the same time. There are triplets and quadruplets depending upon just exactly which hydrogen atom you're looking at, and it has to do with these bond processes. But basically this was, in fact, if you look at the scale here, these are frequency shifts in parts per million. These were very, very tiny effects, and it really took quite a while to be able to do this, but in fact, this was a spectacular advance in nuclear magnetic resonance at that point. I dare say that the thing that really made this work was in fact not doing what's called continuous wave nuclear magnetic resonance, where you either swept slowly the magnetic field or the frequency, but in fact this was pulsed NMR. Pulsed NMR was invented by this person here, Richard Ernst. Now, it used to be that there were a set of meetings every 3 years, I believe it was, and I would meet most of these gentlemen. So I met Richard Ernst. What Richard Ernst did for nuclear magnetic resonance, he is rather than very slowly tickling the nuclear spins, in fact, he would apply a very intense pulse of RF energy, which would tip all the spins by 90 degrees, and then as they processed, they would induce a voltage in a pickup coil, and that's pulsed NMR, and that's, in fact, what Richard Ernst got the Nobel Prize for in 1991. It wasn't in physics. Physics was the original NMR Nobel Prize, but in chemistry, because, in fact, this was mostly useful for organic chemists in particular. That Richard Ernst didn't do this all by himself. He had a partner, and his partner's name was Kurt Wutrecht, and the two of them had done a lot of this work. But when it came time to getting a Nobel Prize, in fact, Kurt Wutrecht did not share the Nobel Prize with his Swiss colleague, Richard Ernst. And so I would meet these guys at these NMR meetings, and I went to Kurt Wutrecht and I said, Kurt, how did you feel when Richard Ernst got the Nobel Prize and you didn't share it with him? You must have been disappointed. He said, no, I wasn't disappointed. I was mad. And so, but it's interesting. What happened, of course, is that Richard Ernst then set out as a man possessed to show that he could do things with NMR that no one else could do. And indeed, he invented a very complicated pulsed NMR sequence which allowed him to determine the three-dimensional conformation of even complex molecules like proteins. So this was a real boon to NMR, and of course, eventually in 2002, Kurt Wutrecht got his own Nobel Prize, and if you look, he's smiling. I think you can't be accepting the Nobel Prize from the King of Sweden without smiling. Anyway, so now we've had 2 Nobel Prizes in chemistry for aspects of NMR, and a Nobel Prize. The original one was in physics. But we're really not done yet, because in fact, I think, I don't know, I was probably not the first one, but people in the early 1970s started realizing that if you applied a magnetic field gradient across the sample which contained the nuclear spins that you wish to study, that in fact you could actually create images with very detailed structure. This is a rather healthy human knee. My right knee is made of titanium, and I don't think you can do those experiments on it anymore. Anyway, so for their work on developing what's called magnetic resonance imaging or nuclear magnetic resonance imaging, Paul Lauterbur and Pierre Mansfield in 2003. Now this is 1 year after Kurt Wutrecht got his Nobel Prize for determining the three-dimensional conformation of very tiny things, proteins, and these two determined the three-dimensional conformation of large biological things like knees. They shared the Nobel Prize the next year. This is the 4th Nobel Prize for some aspect of nuclear magnetic resonance. And if we go back now to what the inventors at NMR said to the press, Felix Bloch, when asked what NMR might be good for, he said, damn little. And of course, his counterpart said maybe one could use NMR to calibrate magnetic fields. And so what I'm trying to show you is that the visionaries that developed these new techniques don't necessarily know what they might be good for. And I think that's something that's worth remembering.